and this is a slab that is one way, because we can see it here. She is supported here by beams or brick walls here and here, and we're gonna say this side has 1 meter, and from here the center of the brick wall or the beam that she supported, here to here we have 4 meters. We can see her in the cut. So for this we have to consider that since it's supported here, we'll have to consider the longer span for this calculation and not the minor span. And we can see what the age, the total depth we should use for this slab. If we use this little equation, this total depth can be estimated by this equation that will help control the deformation on the slab if you use this. So this 4 meters divided by 20 give you 20. Here is 0.2 meters. It is 20 centimeters, and the effective depth we can calculate it. We can consider that is the total depth that we have subtracted by the nominal cover C and half of the diameter that we will get. But this is approximately the total depth less 3 cm, 0.03 meters. So we can get that the effective depth is 0.70 meters. Okay, and for concrete we're gonna use C3037, that is equivalent to the M13. So for the FCD, we know that we use a safety factor that is 1.5, but will give us 20 megapascal. For steel, we're gonna use the A500, and this can be, there are many types of steel on the market. It can be A500, designation can be S500, or you can have a steel for iron rods for FE500. So the characteristic value will be, for the steel, will be 500, and is FYD will have a safety factor. We're gonna use 1.15. So with this data we can start calculating this one-way slab. She's automatically one-way slab, how we can see it, because she's supported in opposite sides, brick walls or beams. That's why, but we could calculate that. So for self-weight, it will be the total depth 0.20 multiplied by the density of concrete 25 that we're gonna use, would give us 5 kilonewton per square meter. For floor finish, we're gonna consider 1, could be another value, could be 1.5, 2 kilonewtons per square meter. We're gonna have a live load, so it's gonna be crossing here, and we're gonna consider 3.5 for the live load. And from this equation, if we check the bigger span divided by the minor span, the 4 divided by the 1, that is giving 4, it's equal or bigger than 2, what is saying that is a one-way slab. So to start calculating the reinforcement for this slab, we're gonna have to check the ultimate limit state for flexure, bending moment, and for shear. So we start factoring the loads for that on the ultimate limit state, factoring these loads. That will be the combination of the permanent loads that is in the Eurocode, calculated by 1.35, plus the variable loads and the live loads that is multiplied by 1.5. When we take this, the self weight of the slab by meter, the floor finish on the permanent load multiplied by 135 plus 1.5 multiplied by 3.5 live load, we get 13.35 kilonewtons per square meter. So this on a simply supported structure, for the moment will be the weight, factored weight, multiplied by L by L divided by 8, what gives you 26 kilonewtons per meter. Since we consider only 1 meter, we're going to consider only 1 meter for the sectioning that we are evaluating. And for the shear, you have the factor weight multiplied by the length. This length is in this case the bigger one because it's supported on this. Normally, in many cases, it will be supported differently to save steel, and in many cases, so it's the shorter span that is considered to calculate this factoring moment and shear moment factor. So 26 kilonewtons, 2 for shear. And so we're gonna have to calculate the reduced bending moment, or we can call it K. Use it in the British standards or in the Eurocode. This K is a non-dimensional moment parameter, the K. I'll call it mil. That is equal to this equation in the Eurocode. We have this on tables. We can calculate it here. The factoring, the moment, factored moment divided by B. That is, we are considering 1 meter, and the effective depth, and multiply by the FCD. Of course, it will have this equation, and we'll get this non-dimensional moment that is equal to this. And we have already to say for economic purpose what is the limit for this reduced bending moment, and so the bending moment we have here has to be less or equal to the limit of bending moment, and this we have on table. This is what we calculate. This is for simply reinforcement. Just, when this happens, it's simply reinforced slab. So this table, for example, this concrete is C30, 37, and the steel steel is A500 or S500 on the table. If we go to the tables, we have this table here. So the 500, the bending reduced moment, the limit is 0.371 for concrete less or equal to 50 to 60. So this is what we get. So we can check, and it's simply reinforced. The value is already determined for this kind of concrete. K1, K2 is table. We have this on Eurocode. K1 0.81 and K2 0.416. With this, we are able to calculate the percentage of the reinforcement that we're gonna need for the main reinforcement, and it's taken from the Eurocode on this equation. Percentage K1 divided by 2 multiplied by K2, well, this multiplied by 1 less from this equation. Okay, we get this value, you can see here, will give us 0.047% for main reinforcement. And the equation to get how much we need for the main reinforcement is this one. The percentage multiplied by B, multiplied by D, multiplied by FCD, divided by FYD. Would give us 3.7 square centimeters per meter. Okay, so the iron rods that we're gonna use, I choose the 10 spaced by 20 centimeters. So the 10 millimeters, because if I choose 8, I get 2.51, that is less than 3.7 that I need. So on this case I'm using the 10, and the fact for this spacing, it's because I like to use for maximum spacing 25 centimeters. This space should be, you can calculate like 1.5 of the total depth multiplied by total depth. So you get the minimum value from the 1.5 multiplied by total depth, or you could use 30 cm, but I like to avoid the future problems, and the maximum I use is for a slab of this magnitude could be 25 centimeters. So the minimum value that I get 1.5 multiplied by the total depth 0.20 or 25, it gives me 25. So when I use it the 25 here for spacing with this, it gives me 3.14. I couldn't use this, so because I need 3.7, so I go to a spacing with 20, 3.93, and here is okay. But after having this, I have to verify the minimum steel by equation of the Eurocode, and that is this one. The minimum reinforcement, it's equal to 0.26 multiplied by FCTM multiplied by the tension zone B multiplied by the effective depth divided by FYK. And this FCTM you get it from the tables too in the Eurocode for this concrete FCTM. So if you go to the tables, you have here FCTM megapascal, and for the concrete C30 37 you go here is 2.9. Okay, so you have there 2.9 multiplied by, we are using 1 meter, multiplied by D, that in this case it's 0.17 meters. Okay. Of course, you pass this since you are getting in square centimeters per meter. When you calculate, you make these multiplications to get that, and divided by FYD. That is the FYD 434 Pascal. So here it gives us 2.56 square centimeters per meter. And to get this for minimum steel reinforcement, if you have put here 8 to be small, not enough, using the same spacing, I want to use the same spacing than in the main. For this case could be another one, but I want to maintain the same spacing, and 2.51 will not be enough for the minimum reinforcement, so I maintain the 10.393. That is the same that I adopt for the main reinforcement. So it's check the main reinforcement, the minimum reinforcement to use is check it for the main reinforcement, so we can maintain, we don't need to increase it. After having this, we go for the distribution bars. The distribution bars that are the main bars were these ones that are along the span. Distribution bar is the ones that are now on the shorter span, along the shorter span for this case. And we know for this distribution will be 20% of that steel. And this 20%, it's just multiplying the steel that was given, 3.7 square centimeters that we calculated, multiplied by 20%, 0.2. They give us 0.74. It's a very small quantity, but for me, I like to maintain the minimum. So that's why I want to maintain the minimum steel. All calculations I do, I maintain the minimum. I get a better design and I avoid other types of issues. In the overall, it's beneficial. So I know the minimum was a phi of 10, spaced by 2393. That's what I locked here. It's much bigger than what I really need here. This case is very small quantity that I'm spending. For the reinforcement on the distribution. Okay, so now for since it is like this, we can get here on the supports some kind that can crack. So for that we calculate some reinforcement on the support. and this is given by an equation that will be the maximum between the minimum reinforcement that we already calculated or 25% of the main reinforcement steel. So whatever is the maximum, that's what we're gonna use. When we calculate this maximum, it ended up to be 2.56. It is the minimum. So it was good for us, the minimum, and we already know is this that we have to adopt. So we're gonna maintain this diameter of 10 millimeters spaced by 20 centimeters. And now for the distribution on the top here on this area that goes from here to here on the top. It's 20% of the distribution on the support that we got, and that is a very small quantity in this case, 0.51, because it's just 20% of what we have calculated. But since I don't want to use steel with a diameter of 6 millimeters for these things, I will, as a rule, I always use the minimum steel that I have calculated, that in this case was 2.56. So I will maintain here in the distribution bars the same kind. That is diameter of 10 spaced by 20, and I was able to get here a very harmonious reinforcement, maintain in all the 20 spaced. Sometimes it's not, it doesn't happen like that, but in this case it was. And the steel I'm using, it's all 10 wolf. So again, was not necessary like that, but I always like to use the minimum steel as a safety, and all my calculations are always 100% on mark, even when you use many kind of softwares that are selling there. They give you exactly this. So here we can see here on the bottom, for the moment, we'll get diameter for the main reinforcement. We'll get a diameter of 10 spaced by 20. That gives this quantity, 3.93 square centimeters per meter, and then the distribution bars give us 10 spaced by 20 here on the bottom. So it should go from here in the support to the other support, here to on the bottom. On the top we needed to reinforce here in the connection with the supports. That can be a brick wall or the beams. So it goes, and this should be a distance from the L divided by 4 at least. In this case, since it's 4 meters divided by 4 gives 1 meter. So it will go from here, this reinforcement there, from here to there, 1 meter. And we were gonna use for this reinforcement in the support diameter of 10 spaced by 20, and for distribution we'll get at least 20% of this. We get the diameter of 10 millimeters spaced by 20. Of course, this is similar in the other side here, the support. So we have checked the bending moment for the flexure in the ultimate limit state. Now we're gonna check the shear to avoid, to see if we need here to use triggers or not. We're not gonna have a need for that. So check for the shear at the ultimate limit state. We know this value that we calculated for shear. That is that was 26, and it has to, this value has to be smaller, less, or equal to the resistance, to the shear resistance, and this shear resistance is equal to this equation, and has to be bigger or equal to this other one, according to the Eurocode. So you can see this in Eurocode at 6.2.2 for members not requiring shear reinforcement. Okay, so we know this value that we calculated. The shear resistance is this one. This value CRD, it's equal to 0.18 divided by a safety of the concrete, that is 1.5. That gives us 0.12. This is in the Eurocode too. We use this equation. This equation has to be smaller or equal to 2. If not, we have to adopt 2. In this case, when we calculate it, this is the diameter in millimeters. When we calculate it, gives 2.08. So it's bigger than this. So it's KO in a meaning that we have to use this value too. We use K as 2. K1, it's a fixed value. And for axial force, we don't have axial force or press stressing, so this is why it's 0 in the equation here. This we don't have axial force on this calculation or press stressing, so this is why it's 0. And from this calculation, in reality, this value, the shear calculated the ultimate limit state, that was 26, has to be smaller than the resistant shear, that in reality is the maximum of this. There is this value here and this one, and the maximum of them. So, and the maximum of them give us this one, 77. So it's checked. It's checked the safety for shear at ultimate limit state. Since we have 26 and this is smaller than 77. Let's check it. So thank you for watching, and this is the reinforcement we can use for this one-way slab.